So welcome back for lecture 4C. And all we're going to do in lecture 4C is just go through a molecular orbital theory review, take a look at some of the topics that we learned in our first course, Chem 1101. So just a real quick review. So molecular orbital theory, remember, uses the concept of a linear combination of atomic orbitals, LCAO, in order to make molecular orbitals. And so a lot of the other theories, if you start looking at Lewis dot structures or VSEPR or hybridization, everything there was still based on atomic orbitals as opposed to molecular orbital theory, which allowed orbitals to spread out over the entire molecule, and we called them molecular orbitals. So those MOs reside throughout the entire molecule. They are considered to be delocalized throughout the molecule and don't just reside on a single atom. Now, occasionally you will see molecular orbitals that are highly focused on a single atom, but that's just kind of where they're at with a limitation where we draw that molecular orbital. So let's look at the simplest molecule you can possibly have, H2, and we'll see how that goes by molecular orbital theory. So an H2 molecule has just two atomic orbitals contributing to the molecular orbitals. One hydrogen has a 1s, the other hydrogen has a 1s orbital on their atoms. Those combine, overlap, and we get our molecular orbital. So they form a sigma bond. Remember, a sigma bond is something that just combines in one location, so kind of coming together like that, as we see in the diagram here. So we have a 1s plus the 1s. They're going to interact in a constructive manner because we can consider them to be waves. So they're going to add together, and we're going to get an increase in electron density between the two atoms. And we have what's called a bonding orbital. So we call that a sigma 1s because it's a simple sigma bond formed by 1s orbitals. Notice here that the energy went down in forming the bonding orbital, and that's very common. It becomes more stable, forming that interaction, and so the energy goes down. Now, we still need to preserve the number of orbitals. So if I take two atomic orbitals and I combine them, I have to have two molecular orbitals that come out of that operation. Our first operation was done by adding the atomic orbitals together. The next molecular orbital that we create is going to be derived by subtracting the two orbitals from each other. And this is what we call an antibonding orbital. So we denote that with a sigma. It is still a sigma interaction because it's still just interacting in a single place. We still have the 1s because it's 1s orbitals interacting, but we're going to put a little star on there to indicate that it is an antibonding orbital. So here's our antibonding orbital here. We've got our 1s, but here we have that they're subtracted from each other. The area where these two orbitals overlap subtracts, and they actually cancel out, and it creates what's called a node. And a node is a region of zero electron density. It's a region of zero electron or orbital overlap, and that creates an antibonding orbital. This destabilizes the orbital itself, and so the energy goes up. And so your antibonding orbital is always going to be higher in energy than your bonding orbital. So in a linear combination of atomic orbitals, we can view that bond as forming between the overlap of the 1s orbitals. Because these orbitals really are just wave functions, we can think of the adding or subtracting as the different types of interference. So when we have our bonding orbital where the two orbitals are adding together, we can consider that to be constructive interference. When we get this, we get a lower energy bonding. Where they subtract, we can consider that to be destructive interference, again, wave functions. And we get that node there where they subtract completely from each other, and you get zero electron density or zero electron probability in that area, and that creates an antibonding orbital. We summarize these by putting together what we call molecular orbital diagrams or MO diagrams. On the outside, we put our atoms. So this is one of our hydrogen atoms. This is the other hydrogen atom. The author just happened to put this hydrogen electron upside down just because they're going to come in here as a pair and go in anti-parallel to each other. You can draw it however you want. This isn't correct. It's not incorrect. It's just a way of doing it. It's I should say it's fully correct, but it's not like the correct way. So when we form our molecule in the center of all these, we're going to form our bonding orbital here. We form our anti-bonding orbital here. We know our bonding goes down in energy. Our anti-bonding goes up in energy. The electrons are always going to fill in an orbital with lowest energy first. And so each of these orbitals can hold 2 electrons, just like an atomic orbital can. So every molecular orbital can still only hold 2 electrons. So I've got 2 electrons total. I've got one from this hydrogen. I've got one from this hydrogen. They both are going to go down here. So at this point, I am only occupying my bonding orbital, and that's why hydrogen has a bond. Now we can look at something called bond order and see numerically or more quantitatively why we have a single bond between 2 hydrogen atoms. Bond order is a very simple calculation that you use with a molecular orbital diagram, and it's as simple as the number of electrons that you've placed into bonding molecular orbitals minus the number of electrons that you've placed in anti-bonding molecular orbitals, and then you just divide that by 2. So here for our hydrogen molecule, we've got one here, one here. I'm sorry, those are my atomic orbitals. I've got 2 electrons in my bonding orbital for the molecule. I've got no electrons in my anti-bonding, so I have 2 minus 0, which is 2. 2 divided by 2 is equal to 1, so I have a bond order of 1, and that equates to a single bond. Let's look at a helium molecule. And what we see is helium has 2 electrons because it has an atomic number of 2, so 2 electrons. So it still only has 1s orbitals, so I have the exact same molecular orbital diagram as for H2. The only thing that's different is the number of electrons I have to fill in. I have 2 electrons from this helium atom and 2 from this helium atom. So if I put in 2 here, I still have 2 more to put in here. That uses up all 4. Now, when I calculate my bond order, I have 2 in the bonding, I have 2 in the anti-bonding, so that's 0, and 0 divided by 2 is 0. So the He2 molecule is not stable, and it's not seen. Now, what if we did something like stripped off a helium atom, an electron from a helium atom? Well, it turns out you can do that in some very high energy areas that are very cold and under a high vacuum, something like space. And this, we do actually see this molecule occurring in space. This is the helium-2 plus ion, so He2 plus. I guess we have it right down there. So one of our helium atoms has 2 electrons, one of them has 1, it doesn't matter which one, but it gives me 3 total electrons. 2 of them go down here in the bonding. The one that's left has to go into the anti-bonding. When I fill in my bond order, I have 2 in the bonding minus 1 in the anti-bonding, so it gives me 1 divided by 2, and it gives me a half bond order. So we do have some overlap. We do have a bond that exists between those 2 helium species. However, it is very weak, which is why helium-2 plus can only exist under very low energy conditions because it does not have a lot holding it together. So, just a summary of what we reviewed in this part of the lecture. Molecular orbitals can be approximated as a linear combination of atomic orbitals, and that linear combination basically means I'm going to subtract their wave functions to get one result and add the molecular orbitals to get the other result. The number of MOs must equal the total number of atomic orbitals, so whatever I put in, I have to get the same number out. When 2 atomic orbitals combine, 2 molecular orbitals are formed. One will be lower in energy, that will be the bonding molecular orbital. One molecular orbital will be higher in energy, and that will be the anti-bonding molecular orbital. The lowest energy molecular orbitals are always filled first. They'll be filled with 2 electrons that are spin paired, one up, one down per molecular orbital. So Hund's rule is always followed. So if you have molecular orbitals that have the exact same energy, they will occupy each orbital singly first before pairing up.